So yeah, welcome again to this workshop organized by HarwellXPS and Elasticity. The Mark just covered a series of techniques that can help us understand the physical structure of the catalyst, such as the morphology, porosity, and the depth profile. And now I'm going to explore a few more of these techniques that help us understand the electron structures of the samples. And not too many, just 5 of them. So let's get these 5 before lunch. First, let's have a look at the UPS, which is ultraviolet photoelectron spectroscopy. Different from the XPS, which has an energy above 1 keV, the ultraviolet spectroscopy is achieved from the UV radiation, which is usually around 20 eV. Because of the low energy, we can only eject the electrons from the valence area and get the information from them. And this will provide some estimates of the density of the states of the material structure and also help us calculate some work function. We know the structure of the atom, which contain the different electrons in the core or valence ions. And if we plot these electrons in a potential energy diagram, you see that the valence orbitals are close to the Fermi level and which have the less energy than those core electrons. And these electrons will give us some fingerprint information of the atoms, and such as the metallic bonding and some other detailed information. And once these electrons absorb the energy from UV radiation, we'll collect them and using the analyzer. So if we rotate the typical XPS spectrum 90 degrees, we can fit well in this diagram. And the valence band area is located in this very low binding energy area. Most of the time, it's difficult to see these fingerprints features with XPS spectrum. And with UPS, we will be able to look closer to this area and work out some key information such as the work function. For example, this is a molybdenum trioxide deposit on the titanium. And these catalysts are used for alkane crackings. So let's look at the XPS of the molybdenum 3D spectrum. Before the hydrogen reduction, we could see this typical doublets of the molybdenum 3D, which belongs to the 6 class of the molybdenum. However, after the hydrogen treatment, we could see the molybdenum oxidation states have been reduced to several multiple lower oxidation states, such as molybdenum 4 class and possibly molybdenum 5 class. This is what we can get from XPS. However, if we use the UPS for the same sample, we could see that after the hydrogen reduction, you see these 2 pumps which corresponding to the pi and sigma bonding of the molybdenum. And these are key features for molybdenum 4+, which is molybdenum dioxide. And we don't see anything such as the molybdenum 5+. And this feature also indicate that on the surface of the molybdenum catalyst, there are either 4+ and the metallic bonding. So this is what the XPS do not observe. And this is a typical UPS spectrum, and this includes two processes. One is the primary process, which is the elastic scattering of the photoelectrons. And these photoelectrons don't lose any energies. Therefore, they provide detailed structure information, and which correlates to their electronic states and has a good approximation of the density of the states. And there's another process in it, which is the inelastic scattering. And this gives us a continuous background because of the loss of the energy. So these two processes superimpose each other. And with this spectrum, we could calculate the work function of the sample. So the work function is difference between the sample Fermi level and the vacuum level of the sample. And normally we apply a bias to the sample to decouple the Fermi level of the spectrometer, and also make sure the secondary electron cutoff is above 0. And then we could see that the work function is actually measurable with the kinetic max and the kinetic energy minimum. So with the total UV source energy minus this difference between these, and we could get the work function of the sample. In terms of how to do it in the spectrum, we can use the secondary electron here and the maximum kinetic energy here. And now let's move to the reals, which is reflection electron energy loss spectroscopy. So when the electron beams with different energies, which could be as low as few hundred eV or up to tens of thousands eV, the energy will be able to hit the electrons in the core level or valence band, and the spectrum is recorded with the reflected electron energy, and the loss is the difference that we are looking for. So with this technique, we could discover the band gaps or some defect sites that appear in the valence bands, and also maybe the oxygen vacancy. One of the surprising things is that the reals can detect the hydrogen, which XPS cannot. For example, in this real spectrum, the primary elastic peak is very high, where we don't see any loss energy. And comparing to the spectra which obtained from few organic materials, you see that for PTFE, which has no hydrogen present in the molecules, we don't see this energy loss at about 1.8 eV. But then with the other organic materials, which all contain different amounts of hydrogen, you can see that the hydrogen energy loss right after the primary elastic peak. Together with this, further down to this energy loss, we could see the concentrations of these aromatic rings, and these peaks are shown as the electrons transferring from the HOMO to LUMO. And we could see that for polystyrene, the light blue one, and the PET, the dark blue spectrum, they all have the conjugated features. As I mentioned, the reels can help us measure the band gap, but depends on the intensity of the electron beam. We will sometimes we could achieve, we could get a good approximation of the band gap. So these are the reels of the titanium. Sorry, it's the reels of the aluminum nitride. We could see that with the increase of the electron beam energy, the shapes are different. At 500 eV, this spectrum increased gradually, and we don't see it's difficult to see the onset of the absorption. However, with the 5 keV and 20 keV, we could see that the energy loss onset start appearing just between 4 and 8, which is more closer to 8 eV. And that helps us to measure the band gap of the aluminum nitride. And when the energy increased to 40 keV, because of the recoil effect, we will be able to see both aluminum and the nitride transition, which overlaps the onset of the band gap. Therefore, it's very hard to determine the position of the band gap energy loss. So it's very important to choose different energy source for this to measure a certain semiconductor band gap. And then also some oxygen latency could be observed with reels as well. This shows the silica reel spectrum. The black one is as we see, and we don't see the feature from here. We only see the onset. Yeah, gas around the 8.3. But with the 2 kV argon cluster etching for 2 minutes, the surface oxygen has been removed from the ion bombarding. Therefore, we see these small features appear below the band gap region. And this is a technique that some of you may be interested when you are about to study the oxygen valency catalytic activity for certain materials, because they play quite an important role in the catalytic reaction. Okay, so next one is about Auger. Phil has covered a little bit Auger. We could see that using even in the XPS background. Here, let me first introduce the Auger emissions chromatography. So when an photon with certain energy hits a core level electron, then this electron leave a hole behind, And another electron from a different core level will fall to this unstable core and give out a certain amount of energy. And if this energy is big enough, it will trigger the third electron from different orbital to absorb it and escape from the orbital orbital. That's the OJ positive electron. So it's an independent magnetic energy with the incident radiation energy. And for this particular transition, we could see that we name it as KL1, L23 is because K is the first hole left from a electron reaction. L is the first electron fall into the hole, and another L is the third electron, which we get it from absorbing that amount of energy. So this technique is very useful, and it helps us understand the thin films and the overlayers for certain materials. For example, here is the Auger spectrum using the electron gun source. And these two are the original spectrum. The different layers of graphene are deposited on the silica wafer surface. And we can see that the more layers of graphene are deposited, the carbon Auger peaks increase. At the same time, because of the oxygen from the titanium are buried, therefore the oxygen Auger peak decrease. From these four are the first differential spectrum with different elements of the Auger spectrum. So for the silicon, you can see that the more graphene are deposited, the silicon Auger will decrease, signal decrease. And the carbon, we will see the increasing of the peak. And oxygen, of course, is from the underneath of the graphene, therefore the decrease of the oxygen Auger peak if more graphene are absorbed. This slide looks similar because also Phil mentioned it. And the previous one was obtained from the electron gun, and this one is obtained from the X-ray source. As we could see that the XPS of copper 2p spectrum here, we can only see that copper 2 plus is standing out because of the satellite peaks. However, the copper metal and the copper 1 plus spectrum give us almost identical location of the 2p peak. Then, if we go to the copper LMM of the spectrum, we could see that a certain shift on there. So that's if you're working with copper catalysts, I know some of you do, and maybe we should look at Auger peaks of copper. This paragraph looks rather complicated, but it's basically shows the different techniques applied on different materials. You can see that XPS can do applied for most of materials, but for certain UPS such or degrees, you could work out their work function, or the time gaps. So let's move on to the next technique, which is Raman. it seems not quite related to the previous one, but we'll see how important this could be. So when an incident light really from a laser shines on the sample surface, most of the scattered lights have the same energy, but only a small amount which have the different energy from the original radiation lights. And these scattering will give us the Raman effect. For example, this third Raman is the molecules absorb the energy and from the ground state to a virtual state, then go back to a different excited state. And the anti-Stokes Raman is the other way around, which the molecule is at certain excited states, then goes to the virtual state and come back to the ground state. There's a difference between the energy that we obtain from the original radiation source. So for the Stokes scattering, the catalyst lies has a longer, bigger wavelength than the original laser source. Therefore, they will shift above. And what we always see from a Raman spectrum is actually half of the spectrum, because the anti-Stokes Raman lines signals are attenuated, and these Stokes Raman most of them usually give us the high intensity and help us to identify the molecular vibration or rotational or other low frequency modes of the molecule. So what is coincident Raman and XPS? So how important this technique is? And we can do this in our and we have this thermal nectar instrument which has the function. So ideally, we would look at the surface of the sample with both XPS and Raman focused on the same point, so that we'll be able to compare that with them. For example, if you work with a very thin layer films, you want to make sure that the films don't have defects, or now the Raman is here to help. Also, if you work with lithium-ion batteries, XPS can give us the information that the surface elements changes after certain amounts of cycles. But because Raman has more depth and through the sample, we would be able to see if the structure changes even under the surface. So here's an example of the boron nitride in thin films. You can see that this is a XPS snap map images showing the boron nitrides are covered and from the precursors, only the red area or green area. So with the point one, we want to look at the XPS spectrum. We'll be able to find both the nitrogen peak and the boron 1s peak here. And then if we look at the high resolution scans of the boron 1s peak, we'll be able to see the chemical oxidation states of the boron, such as boron nitride or nitride. And then the coincident Raman spectrum give us the structural information showing that these boron nitrides are hexagonal rather than cubic. Last one but not least, let's move on to the EasyXAFS. So this is a lab-based X-ray absorption spectroscopy, and the theory is that we energy is tuned to just below a binding energy of the particular electron shell. And by increasing the energy, the electron will have enough to be ejected from the orbitals. And these photoelectrons, due to the quantum mechanical effects, they will provide the local coordination structures around the atoms that they are coming from. So it's like the ripple in the pond. These photoelectrons have the wave functions, and the oscillation will give us the local structures of the electrons interacting with other atoms. And the typical EasyXAFS spectrum is like this. You have this pre-edge where the electrons absorb certain amount of energy and can move from occupied to unoccupied state. Then this near edge area, the shifts and change will provide the oscillation states of the elements. And this oscillation give us the local structures of the lab-based EasyXAFS is rather small, which is less than 2 by 2 meters space, which just fits in a lab across the hall, not like diamond next to us. So with this, we could see that the cobalt K edge EasyXAFS spectrum will collect it and do, depending on the loadings and the concentrations of the elements, with to be a slow process until you get rather a nice smooth spectrum. Yeah, different from the single source. So with us, you can easily access if you don't have the beamline, and then we will help you get a rough idea of the your samples. Then you may try to propose a rather complicated experiments with synchrotron based on some preliminaries results. Yeah. So to summarize and just introduce a couple of techniques that help us understand the electronic structures. And if you're looking at the changes of catalysts before after reactions, then you want to know how the electronic structure changes. Yeah. Try to think some of these techniques besides XPS. And also if you work on some modified surface films deposition and this kind of materials, and also try to explore these kind of options. And I hope me and Mark make you more confused after introducing these many techniques. But if you have any problems or issues, inquiries, just let us know. Then we will work together to help you find the right experiments to carry. Yeah, thanks, and come visit us online or in person, and thank you for your attention.
Realise we are now also on in preview and lunch, but are there any questions? Obviously, do come and talk to HarwellXPS. Not seeing anything coming in online.
I don't want to I don't want to ask a question. I want to make a comment which Shaoliang kind of made. One of our aims when we set up HarwellXPS 5 years ago was that we could act in some way as a gateway to the synchrotron to Dave's high pressure system at the Silicatron. So the EasyXAFS, which we've got in the lab just down the corner, is so much easier to get to access, to use, to set up experiments than in Diamond. And so think of us in that way. When you want to do really complicated experiments, it's probably worth talking to us first to see what we can do to build a case for your application of Diamond.
Is there like a proposal procedure for?
Yeah, so if you go to the website, the HarwellXPS.uk website, register on there, and then you can send in your proposal and we will respond to you.
So one comment, it's not a competitive process. Yeah, if you have any experiments you want to do with us, we will try our best to make it work.
Okay, thank you very much, and I'll echo Phil's comments. Thank you very much.